All right, everyone. Let's look at the solutions to the questions in the worksheet. So the first question is converting Celsius to Kelvin. For the first one, we are asked to convert the initial temperature from Celsius to Kelvin. So reading the information, so initially the mussel was frozen at minus 265 degrees Celsius. So that's the initial temperature. And therefore the final temperature is 27 degrees Celsius. So we need to convert negative 265 degrees Celsius to Kelvin. So don't forget to include the negative sign as well. So that should be negative 265, the Celsius temperature that you want to convert, plus 273, the conversion factor to Kelvin. And that will give you 8 Kelvin for the answer. All right, so include the negative sign when you're doing the conversion. It's quite important. And when you're converting from Celsius to Kelvin, you simply add 273. So final temperature, it's the 27 degrees Celsius that we convert to Kelvin. So that's straight up 27 plus 273 gives you 300 Kelvin for that. The change in temperature of the mussel in degrees Celsius, then it's just subtracting the two. So the temperature went from negative 265 degrees Celsius to 27 degrees Celsius. When you're getting the change in temperature, we usually have a positive change in temperature. Anyway, you usually do final minus initial. So you have 27 minus, or take away, negative 265. And that will give you 292 degrees Celsius. Right? So if, for example, in your calculation, you did negative 265 minus 27, you will find that you will have a negative 292 degrees Celsius in the change in temperature. But we'll just usually get the positive for that. So that usually the change in temperature that we will use in our calculations would always be positive moving forward. So even in our next lecture, when we will also be getting the change in temperature, we'll usually just always have we'll always use a positive change in temperature. So that shouldn't matter much whether you did 27 minus 265 or negative 265 minus 27. Just get the positive answer for your change in temperature. So last question for number 1, what's the change in temperature in Kelvin? So we've seen in the lecture that if you're getting the change in temperature in Celsius is equal to the change in temperature in Kelvin. So you can just write down that the change in temperature in Kelvin is also 292. Just change the unit from degrees Celsius to Kelvin. And that should give you the change in temperature in Kelvin. Alternatively, you can subtract 300 minus 8. You can subtract the temperatures that you've converted in Kelvin. So that's 300 minus 8 Kelvin. You'll also see it's 292 Kelvin. But knowing the fact that if you're getting change in temperature, the Celsius is equal to Kelvin, that saves you from an extra step of calculation. All right. Okay, so feel free to type in any questions in the chat box. Otherwise, we'll just move on to the next questions. If there are no questions in the chat box, I'll be checking periodically, but just feel free to type questions anyway. Even if we've already discussed the solution, we can always go back to that. Right. The second question deals about, expansion of objects when they are heated, and but water has a peculiar behavior. So starting from the higher temperature flask, the one on the rightmost flask, 6 degrees Celsius, we know that water would have expanded, will have expanded there at 6 degrees Celsius. And as the temperature decreases from 6 degrees Celsius to 4 degrees Celsius, water should contract, right? Because temperature decreases, water should contract as usual, but only up to 4 degrees Celsius. At 4 degrees Celsius, ice crystals will start to form. So the ice crystals are more bloated compared to the water molecules, and so the ice crystals will cause the water to expand. Below 4 degrees Celsius, the water will expand until it freezes at 0 degrees Celsius. So we'll see here a pattern. If we go the opposite way, at 0 degrees Celsius, as you warm up the water, the ice crystals collapse. And so at 1 degree Celsius, you have here a smaller volume and the arrow goes down. At 2 degrees Celsius, you'll see a further collapse in the ice crystals, causing the volume of the water to collapse. And that will continue, okay, up to 4 degrees Celsius. So starting from the bloated ice at 0 degrees Celsius, when you heat up the ice crystals will collapse. That causes the ice crystals to contract, and therefore you have this decrease in the volume of the water as the ice crystals collapse, even if the temperature increases up to 4 degrees Celsius. But at 4 degrees Celsius, this is when all the ice crystals would have collapsed, would have totally melted and have become water molecules. And then at that point, as you increase the temperature, the water molecules now start to expand. Yeah. Right. Okay, so as the temperature increases above 4 degrees Celsius, the usual thing happens where the water molecules start to expand, and then therefore you'll see an expansion in the volume of water. Okay, so that's how the illustration should look like. The question is, what is important about the level when the water reaches 4 degrees Celsius? We can see here that's when the water level is lowest. Okay. Water level is lowest at 4 degrees Celsius. That's also where the density of water is greatest, at 4 degrees Celsius. And again, that's because water contracts as its temperature is lowered towards 4 degrees Celsius. At 4 degrees Celsius, ice crystals start to form, and the formation of the ice crystals makes the water expand as it freezes, and the temperature lowers towards 0 degrees Celsius. All right. Okay, right, moving on. So the next question is also about expansion as the temperature increases, but now it's a quantitative question and looking at the physiological example. So metal implants such as stainless steel pin, shown here in the figure, are used to stabilize fractures, but researchers are trying to find composite materials that could replace metal implants. Metal implants, they are good conductors of heat, so they actually expand quite easily. And so a major consideration for the composite material is that it should have a coefficient of expansion similar to that of bone. And the first question asks why the composite material should have a coefficient of expansion as close to bone as possible. Right. So we learned in the lecture that the coefficient of expansion is a property of the material. So bone has its own coefficient of expansion. Stainless steel pin will have its own coefficient of expansion, and the composite material would also have its own coefficient of expansion. And the coefficient of expansion sort of determines how quickly the object expands when it's heated, or how quickly it contracts when it's cooled down. So, of course, if you use a material that has a very different coefficient of expansion compared to bone, then that material, if the coefficient of expansion of that material is much bigger than the coefficient of expansion for the bone, then that material will expand faster compared to the bone when the body heats up. And the expansion, the faster expansion of the material will introduce stress in the bone. And we don't like stress because we've learned before that stress causes strain, which is deformation in the bone. So yeah, so we'd want a composite material with a coefficient of expansion close to the bone, so that the material and the bone sort of expand at approximately the same rate as the temperature increases, or contracts at the same rate as the temperature decreases. Okay, so so you can write here a significantly different coefficient of expansion will cause, maybe I'll just, will cause different expansion rates. And this will introduce stress to the bone. Yeah, so you can answer that question sort of like that. All right, and the next question here, we have a composite material, biocompatible hydroxyapatite, HA. Right, it's being investigated for orthopedic implant applications. Its linear expansion is close to that bone, and the coefficient of linear expansion is given here, 98 times 10 to the minus 6 per Celsius. So at the time the HA pin was implanted in the body, the temperature was 5 degrees Celsius and the length was 3.99 centimeters. Now, when the temperature of the body increases because of a fever, the temperature increases to 313 Kelvin. What we are asked is to find the length of the pin because of the expansion when the temperature increased. Okay, and we'll assume that the body's temperature is homogeneous, meaning the temperature of the body is 313 Kelvin all throughout. So, so that the pin also expands uniformly together with the expansion of the bone. Okay, so let's write down what's given Oh, the information that we know. So this is for question B. Right. We're given the coefficient of linear expansion alpha, 98 times 10 to the minus 6 per Celsius degree. We're also given the initial temperature, 5 degrees Celsius. We're given the final temperature, which is 301.3 Kelvin. Okay, and we're given the initial length of the bone, 3.99 centimeters. So centi, the prefix centi, that means 10 to the minus 2, right? So expand out centimeters, 3.99 centimeters will therefore mean 3.99 times 10 to the minus 2 meters. Or you can just do the conversion by dividing by 100, 0.0399 meters. Okay. The temperatures are different. One is in Celsius. The initial temperature is in Celsius. The final temperature is in Kelvin. So although, we said that we'll be getting the change in temperature, but make sure that the units for your initial and final temperatures are the same. Okay. So you either convert Celsius to Kelvin or Kelvin to Celsius. One clue you can, it doesn't really matter because you'll get the change in temperature anyway, and change in temperature in Celsius is equal to change in temperature in Kelvin. But if you want to be strict about it, you can just look at the unit for the coefficient of expansion alpha. So alpha is given in Celsius, inverse Celsius, Celsius to the minus 1. So if you want to be strict about units, then you can just, you need to convert 313 Kelvin to Celsius. So we'll convert this 313 Kelvin to Celsius. And if you're going from Kelvin to Celsius, do you need to add 273 or subtract 273? If you're converting Kelvin to Celsius, yes, you need to subtract 273. So you have to go 313 minus 273 will give you 40 degrees Celsius. Okay. All right. Okay, so then you can get now the change in length delta L, which is the coefficient of expansion times the original length times the change in temperature. So the change in temperature you can get from here, final minus initial. Change in temperature is equal to 40 minus 5. So that's 35 degrees Celsius for the change in temperature. Okay. So you know everything. Alpha is 98 times 10 to the minus 6 times initial length, 0.0399 meters, times the change in temperature, 35. Yeah. And you have a change in length of 1.37 times 10 to the minus 4 meters. Okay. Right. We are being asked for the final length. Actually, what will the length of the pin be during the high fever? So we are being asked for the final length instead of the change in length. So the final length, so we know the temperature increased. That means the length would have increased. And the amount for which it increased is this change in length that we've calculated. So therefore, the final length will be the initial length plus whatever change in length due to the change in temperature. So your final length should be equal to 0.0399 plus 1.37 times 10 to the minus 4. Right, so your final length should be 0.04 meters. Okay. Okay. All right. Okay, so for the last question here, it says the expansion of bone is 20% that of the expansion of the composite HA from B. So over the same temperature range, estimate the coefficient of linear expansion of the bone. Right. So working out 20% of the expansion of HA. Right, so we already encountered this last time in fluids. So if we put this statement in equation form, 20%, that means 20 divided by 100. Okay? And then this of means a multiplication sign. So 20% of the expansion of HA, that means expansion of HA, this bit expansion of HA, that was the delta L that we calculated earlier. Okay. So we can see here that the expansion of the bone, so delta L of H, the expansion of the bone, that means the delta L of the bone. Okay. The expansion of the bone is, when you say is, that is equal to. Okay. So putting that statement, the expansion of the bone is 20% that of the expansion of HA. Putting that statement into an equation form, we'll see that delta L bone, expansion of the bone, is equal to, or is 20%, 20 divided by 100 of, or times the expansion of HA, delta L of HA. So by putting that statement into the equation form, we can then solve for the expansion of the bone. Right. So for the expansion of the bone, delta L for the bone, that's 0.2 times the delta L due to HA is what we found earlier, 1.37 times 10 to the minus 4. Right. So we can solve for the expansion of the bone. Let's plug that into the calculator. Will be 2.74 times 10 to the minus 5 meters. All right. Okay, once you know the expansion of the bone delta L, we can now go and solve the coefficient of linear expansion of the bone. So what the question actually asks finally is the coefficient of linear expansion of the bone, meaning we need to find alpha for the bone. Right, and we know that the delta L and alpha are related to each other via that equation. The expansion is equal to the coefficient of linear expansion times the original length times the change in temperature. Okay, the problem says that it's over the same temperature range, okay, over the same temperature range as in question B. Okay, and so delta T is also what we got there, 35 degrees Celsius. L0 is the length of the okay, right, so it's the length, it's 3.99 centimeters. Okay, we assume that the pin is embedded over the length of the bone, and we know delta L for the bone. Okay, so to find alpha, we need to isolate, rearrange this. So isolate alpha. Okay, so alpha is tied to L0 and delta T via multiplication on the right-hand side. That means to get rid of L0 and delta T, we need to divide the right-hand side. And whatever you do on the right side, you also have to do on the left side. So you also have to divide the left side with L0 and delta T. Okay. Right. And therefore alpha is equal to delta L over L0 times delta T. All right, the delta L for the bone, we've solved that, which is 20% of the expansion of the HA. So that's 274 times 10 to the minus 5, which we've solved earlier for the bone. So 2.74 times 10 to the minus 5 is the change in length of the bone divided by 0.0399 meters for the original length times the change in temperature, 35 degrees Celsius. Okay. So you'll have there a coefficient of expansion for the bone as 19.6 times 10 to the minus 6 degrees Celsius inverse. All right. Okay, so that's the coefficient of expansion for the bone, which we obtain by first getting the expansion of the bone, delta L, and then using the equation for the this equation, delta L is equal to alpha L0 delta T, to find the alpha, or the coefficient of expansion for the bone. Another shorter way to solve this equation is looking at this equation, delta L is equal to alpha times L0 times delta T. You can see that delta L is directly proportional to alpha, right? That means that if delta L for the bone is 20% the delta L of HA, then the alpha for the bone should also be 20% the alpha of the HA, right? Because they're directly proportional. However, the delta L of alpha of the bone changes will be the same change for the alpha. So you can also solve this by saying that the coefficient of expansion for the bone is 20%. It's 20% of the coefficient of expansion for HA. Okay, so Yeah, so what is given in the problem is that the expansion of the bone delta L is 20% that of the expansion of the HA. So delta L is 20% of HA, but we've seen from this equation that delta L is directly proportional to the alpha. So if delta L is 20%, then alpha should also be 20%, right? So alpha for the bone should also be 20% of the alpha for HA. And then we can just say alpha for the bone is 0.2, 20%, times the alpha of HA, which was given in the problem to be, what's the alpha? Yeah, 98 times 10 to the minus 6 degrees Celsius to the minus 1. And doing this calculation would also give you the same answer for the alpha of the bone, which is actually a shorter way of answering that question. But either method, either solution should work. Okay, and so that's the last question in the workshop. Do you have any questions at all, or any comments? Any question either in the workshop solution or the lectures, or any question at all? No? Yeah, okay, so I don't see any questions in the chat box. So I think we can end the session for today. Thank you for bearing with me and the technical difficulties and sticking with the lecture and the workshop. Yeah, I'll see you on Friday for another lecture on temperature and heat, and enjoy the rest of your day.